Hi everyone, today we'll learn how to integrate functions by completing the square. Let's get right into it. So here we have the integral 3x dx divided by x squared minus 2x plus 5. And we notice that here in the denominator we have a quadratic polynomial. And if you remember, if we differentiate arctangent of x, well, we get a 1 divided by x squared plus 1, which is also a quadratic polynomial in the denominator. So that means that if we somehow write this expression in some kind of form like this, well, we can integrate that and we can get some kind of form of arctangent. We can do that by completing the square here in the denominator. So that means that just by completing the square, we have to get the coefficient next to the x, we have to divide it by 2, we have to square it, and that just leaves us with 1. So that means that if we add and subtract 1 from this denominator, we'll end up completing the square. So that leaves us with the integral of 3 dx divided by, so we'll still have our x squared, we'll still have our minus 2x. Then now I'll add the 1 and I'll subtract the 1, that way we don't actually change the value of anything. And I'll add the 5 that was up there originally. So if we notice, this right here is just going to be x minus 1 squared. And this right here will just be a positive 4. So that means we can rewrite our integral as the integral of 3 dx divided by x minus 1 squared plus 4. Now we see that arctangent has something squared plus 1, whereas our integral has something squared plus 4. But that's a pretty simple fix. We can actually just multiply by 1 over 4 on top and 1 over 4 on bottom, and then that just ends up being the integral of 3 over 4 dx divided by x minus 1 squared divided by 4, and then plus 4 over 4, which is ultimately just 1. So now we see here that we have this divided by 4 on the x minus 1 squared. But we can write 4 as 2 squared. And then we can bring that 2 inside the parentheses as just the expression x minus 1 over 2, all of that squared. And so now we can see a pretty simple u substitution that we can make to make things work out for us. So if we let u equal x minus 1 over 2, well then du is going to be equal to 1/2 dx, which tells us that 2 du is equal to just dx. So using that u substitution, I'll go over here on the left, we will have 3 over 4 on the outside just from over here, times our integral of du times 2 divided by u squared plus 1. And now this 2 and this 4 can cancel, and that just leaves us with 3 over 2 on the outside. And now this is a very, very simple antiderivative. This is just going to be 3 over 2 times arctangent of u, plus c of course. And if we plug in whatever our value of u was, namely x minus 1 over 2, well then that leaves us with the final answer of 3 over 2 arctangent of x minus 1 over 2 plus c. So here we have the integral from negative square root of 2 minus 2 to positive square root of 2 minus 2 of dx divided by the square root of negative x squared minus 4x minus 2. So here we see a quadratic inside a square root on the denominator, and if you remember taking the derivative of arc sine, well, we do end up with a quadratic inside a square root on the denominator. So that means if we can somehow write our integral in that form, we'll get a pretty nice solution. So actually, for the sake of making things look better, I'm going to factor out the negative out of all of these terms. So we'll have the integral of negative square root of 2 minus 2 to positive square root of 2 minus 2 dx, and then we'll have the square root of negative x squared plus 4x plus 2. So now we can use our same method of completing the square, noticing that we have a positive 4 for our coefficient here. So that tells us that we should have 4 divided by 2 squared as our completing the square, and that is just going to be 4. So that means that if we add and subtract 4, we'll get a pretty nice implication. So that tells us that we should have the integral from negative square root of 2 minus 2 to positive square root of 2 minus 2 of dx divided by the square root of negative, and remember we're actually going to add the 4 and subtract the 4 inside the negative here, inside the parentheses. So we'll have x squared plus 4x plus 4 minus 4, that's where we took care of completing the square, plus 2. So now if we analyze this a little bit, well, we see that this right here is going to be x plus 2 squared. And this right here is going to be negative 2. And remember though, that we're negating everything. We're taking the negative of everything. So that means that if we rewrite this integral, we will have the integral from negative square root of 2 minus 2 to positive square root of 2 minus 2. And then we'll have a dx in the numerator. That'll be divided by the square root of. So negating the negative 2, we get positive 2. Negating the x plus 2 squared, we get minus x plus 2 squared. Now we see that we have a 2 inside the square root here for our integral, but only a 1 for the arcsine derivative. But that's a pretty simple fix. We can just multiply by 2 and divide by 2 at once inside the square root, and I'll kind of extend the square root there to show that. So that just leaves us with the integral from the negative square root of 2 minus 2 to positive square root of 2 minus 2 of dx divided by the square root of 2 times, now if we factor it out, we get 1 minus x plus 2 squared divided by 2. And actually this 2 here we can just write as the square root of 2 squared. And now we can bring that inside the parentheses as just x plus 2 divided by the square root of 2, and all of that will be squared. Now this 2 here that we factored out, we can bring outside the square root into a separate square root, and everything else stays in its own square roots. So now I'm going to bring that square root of 2 outside the integral, so we will have 1 over the square root of 2 times the integral from negative square root of 2 minus 2 to positive square root of 2 minus 2, and that will just be dx divided by the square root of 1 minus x plus 2 divided by the square root of 2 squared. And now to match the arcsine derivative, we can just use the u substitution of u is equal to x plus 2 divided by the square root of 2, and that just tells us that du is going to be 1 over the square root of 2 dx. And we actually have the 1 over square root of 2 dx here in our integral, so we don't have to worry about manipulating du. But I do want to change our bounds, so let's figure out what those are going to be. So we have u of negative square root of 2 minus 2, that'll just be negative square root of 2 minus 2 plus 2 divided by the square root of 2. That just leaves us with negative square root of 2 divided by the square root of 2, which ultimately just gives us negative 1. And if we try our upper bound, so u of square root of 2 minus 2, well that just gives us the square root of 2 minus 2 plus 2 divided by the square root of 2. And that is ultimately a square root of 2 divided by the square root of 2, which gives us 1. So those are going to be our new bounds on the integral. So now we end up with just the integral from negative 1 to 1 of du divided by the square root of 1 minus u squared. And now that antiderivative is fairly easy. That is just going to be the arcsine of u. We'll evaluate that from negative 1 all the way to positive 1. And once we do evaluate it, well, we do just end up with the arcsine of 1 minus the arcsine of negative 1. So let's think about these values. Well, what angle inside sine gives us a value of 1? That'll just be pi over 2. And what angle inside sine gives us a value of negative 1? And we subtract that, that is going to be a negative pi over 2. And now we see that that simplifies to a pi, and that is our final answer. That just about wraps everything up. Thank you for watching, and have a great day.